The title of this presentation is Measurement of Ventricular Repolarization using a Novel Q-Dot Microcatheter, a Preclinical Proof of Concept Study. Reentrant ventricular tachycardias depend on local heterogeneity and activation, as well as repolarization. Contemporary mapping techniques generally focus on activation only. Assessment of repolarization using standard catheters is quite challenging. We hypothesized that new microelectrode catheters may be well suited for repolarization time assessment. So our specific study goal was to develop a method to measure local repolarization time using a novel microelectrode catheter. The left ventricles of 5 healthy swine were mapped using a microelectrode catheter during RV-paced rhythm, as well as RA-paced rhythm. The Carter-3 mapping system was used. A low high-pass filter corner frequency was set at 0.5 Hz, and contact force was maintained at 5 grams or more at all times. We recorded unipolar electrograms from all 5 available electrodes on the Q-dot catheter, and this included the large ring and tip electrodes labeled M1 and M2, and the 3 microelectrodes labeled Q1, Q2, and Q3. Repolarization time was annotated empirically at 12 discrete time points. In turn, the repolarization times were used to calculate activation recovery interval. And this ARI is defined simply as the difference between the local repolarization time and the local activation time. And finally, we compare the ARIs with measured ventricular effective refractory periods. These verbs were used as a sort of ARI gold standard for the purposes of these experiments. The left panel shows a schematic of the catheter tip for reference. The right panel shows an example of recordings created using this catheter. This includes bipolar tracings as well as unipolar tracings. The red and yellow arrows indicate the location of the empiric assignment of repolarization times. This panel also shows an example of the measurement of local burp. Now, similar measurements were created in 30 different locations in the left ventricle, each consisting of 12 empiric repolarization time assignments, as well as a verb measurement. The repolarization times were used to calculate activation recovery intervals. Next, each of the 12 calculated ARIs was correlated with the local burp. The best ARI-verb correlation was seen when repolarization time measurement was taken at the earliest absolute peak in the T wave, seen in any of the 3 bipolar leads that incorporated the microelectrodes and the ring electrode. This is highlighted with a yellow arrow. This best ERI-verb correlation is shown in the left panel. The right panel shows an example of an ARI map of a healthy left ventricle that was created using this optimal repolarization time assignment. A standard activation or LAT map is shown as well for comparison. Mapping was done during right atrial pacing. The longest ARIs were measured in the basal septum, and as expected, the shortest ARIs were seen in the basolateral wall, which is the site of the latest activation. In conclusion, we have shown that local repolarization can be measured using microelectrode catheters. The most accurate repolarization timing was derived from bipolar electrograms generated between the ring electrode and any of the 3 microelectrodes. Repolarization annotation was taken at the first absolute T-wave peak in any of these 3 electrograms. So the ability to assess repolarization using the microelectrode catheter opens the possibility of creating repolarization and ARI maps that may further increase our ability to identify areas vulnerable to reentry. Going forward, the repolarization mapping technique described in this work requires validation in disease models, such as ventricular scar.